Hello again, and welcome back to Black Hole Files, where science hums softly in the background and big ideas drift past like drowsy comets. If you've been staring up at the night sky lately, wondering what's out there, well, tonight we're heading somewhere truly magnificent. Jupiter, the giant, the guardian, the striped storyteller of our solar system, bigger than all the other planets combined and stranger than fiction. It spins, it storms, it shields, and it sings in radio waves we can't even hear. So wherever you are right now, tucked in beneath the covers, lying back in your favorite chair, or just floating in thought, I'm glad you're here. Tonight's tale is as vast and slow-turning as Jupiter itself, and just as full of wonder. We'll visit clouds made of ammonia, oceans of metallic hydrogen, and a centuries-old storm the size of Earth. We'll skim past volcanic moons and ice worlds that might hide alien oceans. But don't worry, we'll go gently. Think of this as a guided dream, a bedtime voyage through gravity, gas, and glowing auroras. All right, close your eyes, breathe in deep, and let's begin our journey. To Jupiter. 1. Jupiter's size, mass, and mighty gravity. Jupiter is truly the giant of our solar system, a colossal world so large that about 1,000 Earths could fit inside it. In fact, Jupiter is over 11 times wider than Earth. If our planet were the size of a grape, Jupiter would be as big as a basketball. This immense size comes with tremendous mass and gravity. After the Sun formed, Jupiter scooped up most of the leftover gas and dust, ending up with more than twice the combined material of all the other planets. It has the same basic ingredients as a star, mostly hydrogen and helium, but it never grew quite massive enough to ignite like the Sun. Still, Jupiter's gravitational pull is extremely powerful. Anyone standing at its cloud tops, if that were possible, would feel more than twice the gravity they feel on Earth. Jupiter's super strong gravity has made it a major architect of the solar system. Because it formed early and grew so huge, Jupiter has profoundly influenced the orbits and destinies of other objects. For example, it prevented a planet from forming in the asteroid belt between Mars and Jupiter. Its gravity kept the asteroids stirred up, so instead of merging into a new world, they remain small rocks. Jupiter also acts like a cosmic vacuum cleaner or gatekeeper, greedily pulling in or slingshotting away stray comets and asteroids. Many icy comets that might have barreled into the inner solar system were catapulted to the outer fringes or even out of the solar system entirely by Jupiter's gravitational slingshot. In this way, Jupiter helped shield the inner planets. It has likely safeguarded Earth from countless comet impacts by deflecting or swallowing objects that could have hit us. In 1994, astronomers actually watched Jupiter eat a giant comet. More on that later. At the same time, Jupiter's gravity can occasionally nudge asteroids or comets onto collision courses with the inner planets, so it's not always benevolent. In fact, scientists suspect a disturbance in the asteroid belt, possibly influenced by Jupiter, sent the asteroid that led to the dinosaurs' extinction crashing into Earth ages ago. On balance, though, our solar system might be a much more dangerous place if mighty Jupiter weren't out there acting as a gravitational anchor and shield. Its presence has helped the inner planets maintain stable, almost circular orbits, providing a calm environment for life on Earth to develop. In short, Jupiter's enormous size and mass make it a powerhouse whose gravity shapes the solar system, from sculpting the asteroid belt to flinging comets and even tinkering with the fates of planets. Little Earth truly lives in the realm of a giant. With the exception of the Sun, Jupiter is the most dominant object in our solar system. Logically, and its gravitational influence, make sure we never forget it. 1. Beneath the striped clouds, Jupiter's makeup and the great red spot. From afar, Jupiter is adorned with colorful bands and a famous red spot. But what lies beneath those swirling clouds? Jupiter has no solid ground like Earth does. It's a gas giant, made almost entirely of light gases. In fact, Jupiter's composition is very similar to the Sun's. Its vast bulk consists of about 90% hydrogen and 10% helium, with only traces of other elements. These gases are organized in beautiful striped cloud bands that wrap around the planet. The darker belts and lighter zones we see are actually strong jet streams of Jupiter's atmosphere, racing in opposite directions, east and west. The belts appear brownish or reddish, and the zones whitish because of different chemicals and cloud heights. Jupiter's upper clouds contain ammonia crystals, which form white puffy clouds. Below those, there are likely yellowish-orange clouds of ammonium hydrosulfide, and deeper down, probably dark water clouds. The vivid colors in Jupiter's clouds, shades of tan, orange, and red, may come from sulfur and phosphorus-containing molecules rising from deeper inside. As we descend beneath Jupiter's visible cloud tops, the environment becomes extreme. The atmospheric pressure skyrockets and the gases get hotter and denser. There's no hard surface, only thicker and thicker air turning into fluid. Deeper down, the hydrogen gas gets compressed so much that it behaves like a liquid. In fact, Jupiter holds the largest ocean in the solar system, but it's not an ocean of water. It's an ocean of liquid hydrogen. Further in, around halfway to the center, the pressure is so immense that ordinary hydrogen turns into an exotic form called metallic hydrogen. Here, hydrogen is squeezed until its electrons break free, and the fluid can conduct electricity like a metal. This vast layer of metallic hydrogen, swirling around as Jupiter rapidly spins, a Jovian day is just under 10 hours, is what generates Jupiter's powerful magnetic field, like a giant dynamo. It's an incredible thought. Deep under those pastel clouds, there's a churning metallic hydrogen heart, creating magnetism. And at the very center, Jupiter may have a dense core of heavy materials, rock, metal, and ice. Data from NASA's Juno spacecraft suggests that if a core exists, it's not a neat, solid ball, but rather a fuzzy, diluted core that's mixed with the surrounding metallic hydrogen. This could mean Jupiter's core was partially dissolved or spread out by some ancient colossal impact or by the planet's own dynamics. But even Jupiter's innermost secrets are hidden under crushing pressures that would vaporize any spacecraft long before it got there. So some of this picture remains a best guess. Back up in the visible atmosphere, Jupiter puts on a spectacular show of storms. The most famous of these is the Great Red Spot, a gigantic storm system that has been raging for centuries. This iconic oval storm, colored brick red, is bigger than the entire Earth and has been observed continuously for over 150 years and possibly much longer. Essentially, the Great Red Spot is a colossal anticyclone, a high-pressure storm with winds swirling counterclockwise up to about 400 to 500 miles per hour, 800 kilometers per hour. That's faster than the strongest hurricanes on Earth. It rotates around its center about once every 6 days. What's amazing is how long-lived this storm is. On Earth, storms eventually run into land or colder water and break up. But Jupiter has no land and very little friction. It's all fluid, so storms can persist and even outlast entire human lifetimes. The Great Red Spot has been continually observed since at least the late 1800s, and it may be the same feature that astronomers glimpsed as far back as the 1600s. Imagine a storm that just keeps going and going. What makes the red spot red? Scientists aren't entirely sure. The color might come from chemicals dredged up from deep in Jupiter's atmosphere or altered by the sun's ultraviolet light. Possibilities include organic compounds or sulfur phosphorus molecules that turn reddish at high altitudes. Interestingly, when we look at the Great Red Spot in different types of light, it appears different. More on that later in our multi-wavelength section. In ultraviolet light, for instance, the spot looks very dark because whatever chemical gives it that red hue strongly absorbs UV radiation. In infrared images, the Great Red Spot isn't as prominent in color, but we can tell it's a cold region with high clouds. We do know the red spot is extremely tall. Juno's measurements show it extends roughly 200 miles, 300 plus kilometers, above the surrounding cloud deck. That means this single storm reaches deeper than the altitude where water clouds form and well, below where sunlight penetrates. It's like a massive column towering through a huge chunk of Jupiter's sky. The red spot persists, partly because it's trapped between two jet streams that move in opposite directions, which may act like curbs to keep it spinning in place. And Jupiter's internal heat likely helps keep it alive. Jupiter emits a lot of heat from inside, driving vigorous convection, rising and falling gas that can feed such storms. Over the past decades, observers have noted the Great Red Spot shrinking a bit and changing shape. It used to be wide enough for two Earths, and now it's a bit smaller than that. But it remains the largest storm in the solar system, a grand, swirling red vortex that embodies Jupiter's wild weather. Jupiter's atmosphere is filled with other storms and features too. There are white ovals, brown barges, and even smaller red spots. One nicknamed Red Spot Junior appeared after smaller storms merged. Enormous lightning storms flash deep in Jupiter's clouds, and at the poles, Juno found densely packed cyclones arranged in geometric patterns. Jupiter is a dynamic, stormy world. Beneath the pretty bands is a restless, rotating atmosphere that produces features like the Great Red Spot, a storm so vast and long-lived that it boggles the mind. And all of it sits atop a planet made of gas and liquid, with mysteries like metallic hydrogen oceans and fuzzy cores hidden far below the cloud tops. Jupiter is as exotic beneath its clouds as it looks from the outside, a true titan of swirling gases and unearthly storms. 2. The Shoemaker-Levy 9. Comet crash. Jupiter takes a hit. In July 1994, humanity witnessed a dramatic cosmic collision that showed just how powerful Jupiter's gravity can be. A comet named Shoemaker-Levy 9, SL9 for short, had been captured by Jupiter's gravity and torn into pieces, and in that week of 1994, its fragments slammed into Jupiter, one after another. It was the first time we ever saw a collision between two solar system bodies in real time, and Jupiter was the stage for this violent event. But what caused this impact, and what did we learn from it? Shoemaker-Levy 9 was originally a normal comet orbiting the Sun, essentially a large, icy snowball. But in 1992, it strayed too close to Jupiter. The giant planet's gravity grabbed the comet and pulled it into orbit around itself. Not only that, Jupiter's tidal forces, the difference in gravity across the comet, were so strong that they ripped the comet apart. The term Roche limit refers to the distance within which a planet's gravity will shred an object held together by its own gravity, and SL9 passed well inside Jupiter's Roche limit. The once intact comet was fragmented into a chain of 21 smaller chunks. For 2 years, these fragments stayed in an unstable orbit around Jupiter. Then calculations showed an alarming prediction. The string of comet pieces was on a collision course. In July 1994, they would crash into Jupiter's southern hemisphere. Sure enough, between July 16th and July 22nd, 1994, fragment after fragment of Shoemaker-Levy 9 plummeted into Jupiter at speeds of about 60 kilometers per second. Since they hit on Jupiter's far side, as seen from Earth, astronomers didn't witness the impacts live, but within minutes, Jupiter's rotation brought the impact sites into view. What they saw was astonishing. Dark bruises and plumes in Jupiter's atmosphere, some of the impact scars larger than Earth in size. The explosions were enormous. Each fragment created a fireball that rose high above the cloud tops. One of the larger pieces, for example, created a plume nearly 1,200 miles high and left a black mark over 7,000 miles across on Jupiter's clouds, many times the size of Earth's diameter. These scars persisted for weeks, looking like soot smudges on Jupiter. It was a stark reminder of Jupiter's role as a cosmic impact magnet. So, what caused the Shoemaker-Levy 9 impact was essentially Jupiter's gravity, first capturing and shredding the comet, then sending the pieces hurtling into the planet. But what did we learn from this event? Quite a lot. For one, it confirmed that huge impacts still happen in the solar system, not just in the distant past. If Jupiter hadn't been there, that comet might have wandered into the inner solar system. Instead, we got to see it safely crash into Jupiter, possibly sparing the inner planets from a potential hazard. The event also gave scientists a golden opportunity to study Jupiter's atmosphere. As the comet fragments exploded like gigantic bullets penetrating the atmosphere, they dredged up material from deeper layers and created superheated fireballs. Telescopes on Earth, as well as the Hubble Space Telescope and other instruments, analyzed the light from those fireballs and the splash debris. This allowed scientists to detect chemical compounds in Jupiter's atmosphere that are normally hidden. For instance, the impacts produced molecules like ammonia and hydrogen sulfide in quantities that could be measured, confirming those substances in Jupiter's air. Even more importantly, astronomers detected water. During the collisions, water from either the comet itself or Jupiter's deep atmosphere was hurled into the stratosphere, the upper atmosphere of Jupiter. There had been debate about whether Jupiter had any water deep down. These impacts gave a clue that water was present. In fact, years later, observations with the Herschel Space Observatory showed that Jupiter's stratosphere still contained extra water, concentrated mostly in the southern hemisphere where SL9 hit. About 95% of the water in Jupiter's stratosphere was delivered by the comet impact. This was clear evidence that the comet had enriched Jupiter with water. The SL9 impacts also taught us about Jupiter's weather and energy. The dark scars we saw were thought to be debris of the comet and chemically altered material from Jupiter, like carbon black or sulfur compounds, flung high into the atmosphere. By watching how these dark patches spread and faded over days and weeks, scientists could track high-altitude winds on Jupiter, kind of like dropping dye in a river to see the currents. We learned that Jupiter's stratospheric winds dispersed the impact debris far and wide. Additionally, instruments observed radio emissions and auroras from Jupiter during the impacts, giving insight into how Jupiter's magnetic environment responded to a sudden influx of energy and particles. Another lesson was a bit humbling: planetary defense. Shoemaker-Levy 9 was a wake-up call that giant impacts are not just ancient history. If a comet of similar size were on course for Earth, the damage would be catastrophic. Seeing Jupiter absorb such blows, the energy of the impacts was staggering, collectively on the order of 10 to the power of 8 megatons of TNT, underscored Jupiter's role as a cosmic vacuum cleaner and reminded astronomers to keep vigilant eyes on the skies for potential Earth impactors. In summary, the Shoemaker-Levy 9 event was caused by Jupiter's massive gravity, corralling and destroying a comet, and it revealed a treasure trove of information. We confirmed Jupiter's atmosphere has ingredients like water, with most of Jupiter's stratospheric water vapor coming from that very crash. We learned about impact physics and Jupiter's winds, and we gained a vivid example of how Jupiter protects, and sometimes menaces, the inner solar system. The sight of those dark impact scars on Jupiter, each a few Earths across, was poetic evidence that Jupiter, with its mighty gravity, both influences the solar system's layout and bears the brunt of cosmic collisions. Jupiter still wears the battle scars on our behalf, and Shoemaker Levy 9 showed us that in spectacular fashion. 3. Jupiter's magnetic field and radiation belts, risks and shields. Jupiter not only has supersized gravity, it also boasts an extraordinarily powerful magnetic field, the strongest of any planet in our solar system. In fact, Jupiter's magnetic field is like an invisible force field that would dwarf the Sun in size if we could see it. It forms a magnetosphere, a magnetic bubble around Jupiter that extends vast distances into space. How does this magnetic field work? Deep inside Jupiter, as we mentioned, lies a layer of metallic hydrogen swirling rapidly due to the planet's fast rotation. This creates a giant electrical dynamo, generating a magnetic field 10 to 20 times stronger than Earth's on average, and in some regions much more. Jupiter's magnetic field lines loop out of the planet near the North Pole and re-enter near the South Pole, just like a huge bar magnet, but one that is tilted and offset a bit from Jupiter's rotation axis, making the field a bit lopsided and uneven. This immense magnetism has some spectacular effects. For one, it traps charged particles like electrons, protons, and ions that come either from the solar wind or from Jupiter's volcanic moon, Io. Spinning around Jupiter, these particles form intense radiation belts, zones of high-energy radiation akin to Earth's Van Allen belts, but far more extreme. Near Jupiter, the radiation environment is unbelievably harsh. The energetic particles zip along magnetic field lines and can slam into anything in their way with damaging effects. For example, Jupiter's innermost moons, especially the ones close to the planet, get bombarded by intense radiation trapped in the magnetic field. Any spacecraft venturing near Jupiter has to be designed like an electronic tank, with heavy shielding to survive the particle onslaught. The Juno spacecraft, for instance, carries a titanium vault to protect its sensitive electronics from Jupiter's wrath. Even so, over time the radiation can degrade instruments. The environment close to Jupiter is often compared to the radiation inside an unshielded nuclear reactor. It's that intense. For Jupiter's moons, this radiation is a serious factor. Take Europa, for example. It orbits within Jupiter's radiation belts, and its surface is continually bathed in high-energy electrons and ions. This is bad news for life on the surface, which is why any Europan life, if it exists, is probably safe under ice. However, the radiation can also create chemicals on Europa's surface, like oxidants, which might be food for microbes in the ocean below if those surface chemicals get transported downward. So radiation is a double-edged sword, destructive, but chemically useful. Jupiter's closest large moon, Io, is actually a source of much of the radiation. More on Io later. Its volcanoes spew ions that get accelerated in the magnetic field. Ganymede, Jupiter's largest moon, interestingly has its own mini-magnetic field, which gives it a tiny protected magnetosphere inside Jupiter's, a magnetic safe zone that shields parts of Ganymede's surface from Jupiter's radiation. This makes Ganymede somewhat unique and a bit more hospitable compared to Europa or Io, radiation-wise. Now, Jupiter's magnetic field isn't all bad for its moons. In fact, in some ways, it offers protection, primarily from outside threats. Jupiter's magnetosphere is so large, it extends millions of miles toward the Sun, and even beyond Saturn's orbit on the night side, that it acts as a giant electromagnetic shield. It deflects the solar wind, the stream of charged particles flowing out from the Sun, carving a cavity in it. This means that Jupiter and its inner moons reside inside this magnetic bubble, largely sheltered from direct solar wind impacts. By the time the solar wind reaches the moons, it's mostly diverted around the magnetosphere. Moreover, Jupiter's presence can shield the moons from the worst of the galactic cosmic rays, extremely high-energy particles from outside the solar system. Scientists modeling radiation on Europa found that Jupiter's bulk and magnetic field significantly reduced the cosmic ray dose Europa would otherwise get. In other words, while Jupiter's magnetosphere fills the space near the planet with dangerous radiation, it also blocks a lot of external radiation from reaching the moons. A bit like a big magnetic umbrella, it protects from the rain, cosmic rays, solar wind, but has its own sparks flying around under it. For example, researchers found that thanks to Jupiter's shielding, chemicals or potential signs of life just a few feet beneath Europa's surface would remain intact for longer, not erased by cosmic rays. Earth, by comparison, without a strong magnetic field on Mars, cosmic radiation penetrates deeply and can destroy organics. Europa, tucked in Jupiter's magnetosphere, has an advantage in that sense. One dramatic manifestation of Jupiter's magnetic field is its auroras. At Jupiter's poles, gorgeous auroral lights shine in ultraviolet and infrared, and even X-rays. These auroras are hundreds of times more energetic than Earth's northern lights. They occur when charged particles spiral down along Jupiter's magnetic field lines and crash into the upper atmosphere near the poles, causing gases to glow. Some of these particles come from the Sun, like Earth's auroras, but many come from Io's volcanic emissions being funneled along magnetic lines. Jupiter's auroras are so strong that the brightest ones are caused by its moons. For instance, Io, Europa, and Ganymede each create a little footprint, aurora, on Jupiter by their magnetic connection. Standing under Jupiter's auroral oval would be like witnessing a permanent, massive northern lights show. Though you wouldn't want to stand there, the radiation would be lethal. For spacecraft and future explorers, Jupiter's magnetic field and radiation belts pose a significant risk. Any mission that spends time near Jupiter has to contend with potential damage to electronics and even materials. The Pioneer and Voyager probes in the 1970s got a taste of it. Voyager 1's instruments experienced false triggers from radiation. The Galileo orbiter in the 1990s had several unexplained reboots thought to be caused by radiation hits. Juno, which arrived in 2016, takes a highly elliptical polar orbit specifically to dodge the worst of the radiation. It swoops in quickly, gathers data, and zips out, minimizing time spent in the lethal belts. Any future crewed missions orbiting Jupiter would almost certainly have to stay far out, perhaps near Callisto's orbit, which lies outside the fiercest radiation zones, to be safe. In summary, Jupiter's magnetic field is a powerful engine fueled by the planet's rotating metallic hydrogen interior. It creates a huge magnetic bubble that on one hand traps radiation, creating deadly belts that threaten moons and spacecraft, but on the other hand, shields the system from external particle radiation. It gives Jupiter spectacular auroras and ties the planet and moons together in an electromagnetic dance. For the moons, Jupiter's magnetic embrace is both a hazard and a guardian. It blasts their surfaces with charged particles, yet also provides a protective cocoon from the outside cosmic storm. Any spacecraft venturing into this realm must respect Jupiter's magnetic might It's the biggest force of its kind in the solar system, after the sun's magnetic field itself. 4. Seeing Jupiter in different lights: infrared, ultraviolet, and more. To our eyes, Jupiter is already fascinating. Those colorful bands, the great red spot, the shining moons. But human eyes see only a small slice of the electromagnetic spectrum. Jupiter has been observed in many invisible kinds of light, from infrared to ultraviolet, radio waves to X-rays, and each reveals new secrets. By using different parts of the spectrum, scientists essentially X-ray Jupiter, check its temperature, and even peer through its clouds. So, what have we learned by looking at Jupiter and its moons in these different wavelengths? Infrared IR light is crucial for studying Jupiter because it tells us about heat. Jupiter is actually warm. It emits about twice as much energy as it receives from the sun. This means it has an internal heat source, leftover heat from its formation, and possibly ongoing slow contraction. In infrared images, we effectively see Jupiter's own glow, especially at wavelengths where the sunlight is not overwhelming. One big discovery from infrared observations is that Jupiter's atmosphere isn't the same all over. The cloud layers have holes and variations. For example, astronomers in the 1960s first detected strange hotspots on Jupiter in infrared. These correspond to areas in the atmosphere, like certain patches in the belts, that are relatively cloud-free, allowing heat from deep inside to escape and glow in IR. In visible light, some of those areas appear as dark patches, like the so-called brown barges in Jupiter's belts. But in thermal infrared images, those patches shine bright, indicating they are windows into a warmer, deeper layer. This was an important clue that Jupiter's belts and zones differ in more than color. They differ in height and thickness of clouds. By using infrared telescopes and instruments, including those on spacecraft like Voyager, Galileo, and currently Juno, and even the new James Webb Space Telescope, we can map temperature and composition. Infrared spectra have shown us that Jupiter's atmosphere contains gases like methane, ammonia, and water vapor. In fact, the detection of Jupiter's water in deeper layers was significantly improved by IR observations of the Shoemaker-Levy 9 impact fireballs in 1994, and later by the Herschel Space Observatory, as we discussed. Infrared images have also been used to watch storm activity. When a big storm erupts deep in Jupiter, like the formation of a new white plume, infrared monitoring can see the temperature changes and how the upper clouds cool or warm. One of the most stunning things IR has shown us recently is Jupiter's auroras in a different light. We usually see auroras in UV or visible on Earth, but Jupiter has a strong IR aurora as well. A special molecule called H3+, trihydrogen, forms in Jupiter's upper atmosphere and gives off infrared light in auroral regions. The James Webb Space Telescope captured breathtaking IR images of Jupiter's polar auroras glowing like ethereal rings of fire around the poles. These IR auroras taught us about how heat is deposited in Jupiter's upper atmosphere. Interestingly, the IR views of aurora showed details that didn't appear in UV, different wavelengths highlighting different altitudes and particles in the aurora. Now let's talk ultraviolet, UV, light. UV is higher energy than visible, and Jupiter's atmosphere and magnetosphere have many UV secrets. The Hubble Space Telescope has taken many UV images of Jupiter, especially of its auroras. In UV, Jupiter's auroral oval shines brightly, revealing dynamic patterns as the magnetic field is excited by solar wind or Io's influence. We learned that Jupiter's auroras are not only huge but also persistent. Unlike Earth's that come and go with solar activity, Jupiter's main auroral rings are fed continuously by its rotating magnetic field and Io's contributions. Hubble's UV cameras even caught the glow of auroral footprints of Io, Europa, and Ganymede, appearing as little bright spots that follow those moons' magnetic connect points on Jupiter. This confirmed the electric currents flowing between Jupiter and those moons, especially Io. Additionally, UV observations of Jupiter's north polar flickering aurora helped scientists realize that some of Jupiter's auroras pulse independently of the solar wind, likely due to internal plasma processes. UV observations have also been used to detect chemicals and even water plumes. For instance, scientists suspect that Europa sporadically shoots out geysers of water vapor through cracks in its ice. Hubble in the UV has looked for evidence of these by observing Europa's limb as it passes in front of Jupiter. Any extra hydrogen or oxygen from water could absorb certain UV wavelengths. In 2012 and 2016, Hubble found hints of these plumes in UV images, suggesting that multi-wavelength observations might catch what visible light can't. The plumes would be nearly invisible in regular light. On Ganymede, Hubble's UV observations made a groundbreaking discovery. By watching auroral glows in Ganymede's thin atmosphere, scientists inferred the presence of a large subsurface ocean. How? They saw that Ganymede's two auroral bands, caused by its own magnetic field, rocked back and forth, less than expected as Jupiter's magnetic field changed. A conductive saltwater ocean under the ice was buffering the magnetic field changes, reducing the auroral motion. This was the first evidence for Ganymede's hidden ocean, all gleaned from far ultraviolet observations. So UV helped discover an ocean on a moon. Moving beyond infrared and ultraviolet, we have radio waves and microwaves. Jupiter has been known to emit radio waves since the 1950s. It's a noisy planet. There are two main kinds: radio bursts from the magnetic field, especially influenced by Io, and steady microwave emissions from the deep atmosphere. The bursty radio emission, detected at decameter wavelengths, was actually how scientists first realized Io affects Jupiter. They noticed the radiostatic from Jupiter strengthened when Io was at certain positions in its orbit, meaning Io was somehow causing charged particles to gyrate and emit radio waves. This told us there's an electric interaction, now known to be the Io flux tube connecting Io and Jupiter's magnetic field. The steady microwave emission, on the other hand, comes from Jupiter's warm, deep atmosphere. Different microwave frequencies can poke to different depths because gases like ammonia absorb microwaves. NASA's Juno spacecraft carries a microwave radiometer that listens to these frequencies. With Juno's microwave observations, scientists created a 3D picture of ammonia distribution inside Jupiter. They found that the equatorial zone is ammonia-rich high up, and that ammonia levels vary with depth in other latitudes, overturning the assumption that everything was well mixed below the clouds. Juno discovered phenomena like mush balls, essentially slushy hailstones of ammonia and water, that might be forming in mid-atmosphere and carrying ammonia deeper, explaining why mid-latitudes have less ammonia gas above. This insight came from combining microwave data with models, a direct result of looking at Jupiter in wavelengths far beyond visible. And what about X-rays? Yes, Jupiter even emits X-rays, particularly in its auroras. Chandra and XMM Newton X-ray observatories have watched Jupiter and found that the polar regions crackle with X-ray flares. These come from heavy ions, like oxygen and sulfur, crashing into the atmosphere, ions that ultimately originate from Io's volcanic material and get accelerated in Jupiter's magnetosphere. Studying these X-ray aurora pulses, which can be rhythmic every few minutes, has taught us about oscillations in Jupiter's magnetic field and how energy from the solar wind or internal processes is dumped into the atmosphere. It's pretty wild to realize the same planet that emits radiostatic and infrared heat also flashes in X-ray. But that's Jupiter, a true multi-wavelength wonder. Jupiter's moons have also been studied in various spectra. We mentioned Ganymede's UV aurora revealing an ocean. Europa has been examined in infrared spectroscopy, which found evidence of various ices and salts on its surface, important clues hinting at the ocean's composition beneath. Infrared and radar instruments, like on Galileo, found that Europa's ice shell is likely water ice with some magnesium sulfate salts, kind of like Epsom salt, and perhaps sulfuric acid mix on the surface. These compounds absorb and reflect infrared light in telltale ways. Io, being so hot, glows in infrared vividly. The Galileo spacecraft and ground-based telescopes have taken infrared images of Io that show dozens of volcanic hotspots scattered across its surface. Some of Io's lava flows were so hot that they emitted more infrared than any lava on Earth, indicating ultramafic lavas possibly, very magnesium-rich. In fact, visible light cameras on Voyager first saw Io's eruptions, but infrared observations since then have been critical to monitor Io's volcanic activity night and day. Even when Io is in Jupiter's shadow, volcanoes still glow in IR. Recently, Juno's JIRAM infrared mapper captured a breathtaking image of Io's entire surface in infrared, mapping its many erupting volcanoes as bright spots. And when one of Io's volcanoes had a massive outburst in late 2022, a small telescope on Earth detected a brightening in the Io plasma torus, a ring of ionized gas around Jupiter from Io, essentially seeing the volcano's effect by its ultraviolet glow in the torus. This cross-wavelength detective work, optical telescopes seeing sodium from Io, UV detecting sulfur ions, infrared seeing the heat, gives a full picture of Io's volcanic mood swings. To sum up, observing Jupiter in different parts of the electromagnetic spectrum is like looking at a multi-layered painting under different lighting. New patterns emerge each time. In infrared, we see Jupiter's. Heat and can peer beneath cloud tops, discovering hotspots, measuring auroras, and mapping storms' heights. In ultraviolet, we catch energetic processes, auroral displays, magnetospheric interactions, and surface chemistry hints, like water plumes and thin atmospheres. In radio microwave, we probe the deep interior and listen to Jupiter's magnetic heartbeat and Io's contributions. In visible light, of course, we see the familiar bands and spots, and in X-rays, we witness the highest energy assaults on Jupiter's atmosphere at the poles. Each wavelength range has taught us something unique, from confirming subsurface oceans on moons to detailing the structure of Jupiter's storms and the contents of its clouds. It's a reminder that there is much more to a planet than what our eyes can see. By extending our vision across the spectrum, Jupiter and its moons have become richer, more understandable worlds, almost like reading additional chapters of a book that was once stuck on the first page of visible light. 5. Could Jupiter's moons harbor life, and what makes Europa, Ganymede, and Callisto special? While Jupiter itself is a hostile ball of gas and storms, some of its moons rank among the most intriguing places in the solar system in the quest for life. In particular, the icy Galilean moons, Europa, Ganymede, and Callisto, have caught scientists' attention because they appear to have something essential for life as we know it: liquid water oceans beneath their surfaces. Could there be living things in those dark oceans? And are these moons suitable for future exploration, even habitation? Let's take a closer look at each. Europa, the ice world with an ocean beneath. Europa is often considered the top candidate for life in Jupiter's realm. It's about the size of Earth's moon, but unlike our cratered dry moon, Europa is an ice-covered sphere with a smooth young surface, crisscrossed by dark streaks and cracks. For decades, scientists suspected that beneath Europa's frozen crust lies a global ocean of liquid water. The evidence has piled up. Europa's surface is made of water ice, and it's very smooth, few craters, suggesting the surface has been resurfaced by something, likely liquid from below. The Galileo spacecraft in the 1990s provided a critical clue via its magnetometer. It detected a disturbance in Jupiter's magnetic field near Europa, the kind you'd get if a conductive fluid, like salty water, was present under the surface. This strongly supported the ocean idea. Today, we're pretty confident that Europa has a salty ocean estimated to be perhaps 60 to 150 kilometers, 40 to 100 miles, deep, lurking under an ice shell, maybe 15 to 25 kilometers thick. That ocean could contain more than twice as much water as all of Earth's oceans combined. Why is Europa's ocean liquid? Mainly because of tidal heating. Europa is in a gravitational tug-of-war as it orbits Jupiter and is in resonance with Io and Ganymede. Jupiter's gravity flexes Europa's interior, generating heat. This heat keeps the ocean from freezing solid. Now, life as we know it needs water, chemical building blocks, and an energy source. Europa certainly has water. What about the rest? The building blocks, elements like carbon, nitrogen, etc., likely exist. Comets and meteorites deliver organics, and some may be in Europa's initial makeup. Energy is trickier. Sunlight doesn't reach Europa's ocean, so any life would need another energy source, like chemical or thermal energy. Scientists think Europa's ocean floor might be in contact with warm rock, potentially even hydrothermal vents, like the vents on Earth's ocean floors that support rich ecosystems without sunlight. If Europa has hydrothermal activity, hot water reacting with rock, it could release nutrients and energy, chemical gradients, into the ocean, providing a potential buffet for microbes or other simple life. Europa's surface is also blasted by Jupiter's radiation, which breaks apart molecules and could create oxidants. These oxidants, like oxygen or peroxide, could settle on the ice and eventually get transported down into the ocean, say, by the ice shell cycling or cracks opening. If that happens, they'd provide chemical energy, essentially food, for life in the ocean. All these factors make Europa extremely interesting. It's often said that Europa's ocean might be one of the most habitable environments beyond Earth in our solar system. Of course, we don't know if anything lives there. It could be completely sterile. But it's possible that microbes, or something like alien fish, if we let our imagination free, though complex life is less likely, could exist in that dark ocean, feeding off chemical energy from the seafloor or from surface oxidants. The prospect is exciting enough that NASA is sending a dedicated mission, Europa Clipper, set to launch in 2024. Europa Clipper will orbit Jupiter and make dozens of close flybys of Europa using ice-penetrating radar to sound out the ice thickness, magnetometers, and gravity measurements to confirm the ocean's characteristics, and cameras and spectrometers to map the surface in detail and sniff for any plume activity. We're essentially going to give Europa a full checkup to assess its habitability. If Europa looks promising, the next step might even be a lander to drill through the ice, or sample a geyser if one is venting water to space. Ganymede, the giant with a hidden ocean and magnetic personality. Ganymede is the largest moon in the solar system, bigger than the planet Mercury. It's so large that if it orbited the Sun instead of Jupiter, it could be considered a planet. Ganymede is unique among moons because it has its own magnetic field generated by an internal dynamo, likely from a liquid iron or iron sulfide core. This internal magnetic field creates auroras in Ganymede's thin oxygen atmosphere. Importantly, Ganymede also shows evidence of a subsurface ocean. Galileo's magnetometer data indicated that Ganymede's magnetic field was being influenced by something conductive near the surface, consistent with an ocean beneath the ice. And as mentioned, Hubble's observation of the shifting auroras clinched the case for a saltwater ocean about 100 kilometers below the surface. However, Ganymede's ocean is quite different from Europa's. It's believed to be sandwiched between layers of ice, a thick ice crust above, and possibly more ice below, between the ocean and the rocky mantle. Think of a club sandwich with ice layers and ocean as the filling. This means the ocean may not be in direct contact with the rocky seafloor if high-pressure ice forms at the bottom. That could limit the chemistry. For life, contact between water and rock, like hydrothermal vents, is often considered beneficial. Also, Ganymede's ice shell is very thick, maybe 150 kilometers or more, much thicker than Europa's 20 kilometers. That thick ice might make it harder for nutrients on the surface to get down to the ocean and for any life's byproducts to ever reach the surface. Additionally, Ganymede's surface doesn't appear to have active geysers or many fresh young features. It's a mix of very old, cratered, dark regions and somewhat younger grooved terrain, but not nearly as dynamic as Europa's surface. This suggests that Ganymede's interior is not as geologically active as Europa's. So could Ganymede harbor life? It's not out of the question. It has water, lots of it, and likely the essential elements. But the energy sources might be sparse. If the ocean is sandwiched away from rock, and if little from the surface gets down, it could be more like a stagnant layer of water. Some models suggest Ganymede's ocean might even be layered with different phases of ice, potentially even multiple ocean layers. Because as you go deeper, weird high-pressure ice forms, which could separate layers of liquid. It might be a less cozy environment than Europa's comparatively shallower ocean. That said, Ganymede is still very interesting, and it's a target for exploration. The European Space Agency launched the JUICE, Jupiter Icy Moons Explorer mission in 2023, which will arrive at Jupiter in 2031 and eventually go into orbit around Ganymede. JUICE will study Ganymede's ocean, magnetic field, geology, and habitability potential. Even if life is unlikely, Ganymede is attractive for other reasons too. For instance, its magnetic field and lower radiation environment could make it a candidate for a human base in the distant future. Callisto is another candidate, which we'll get to. Ganymede's own magnetosphere could help protect future explorers from Jupiter's radiation to some extent. Callisto, an ancient world of craters and an ocean. Callisto is the outermost of the big Galilean moons. It's about the same size as Mercury as well, but very different from Ganymede. Callisto's surface is heavily cratered and ancient. In fact, it's one of the most cratered surfaces in the solar system, looking like a cosmic punching bag. This tells us that Callisto's interior has been quiet for billions of years. Unlike Europa or Io, Callisto shows no signs of resurfacing or major geological activity. It's essentially been dead internally for a long time. However, intriguingly, Galileo's measurements hinted that Callisto, too, might have a subsurface ocean. The evidence is similar. Changes in the magnetic field around Callisto that suggest the presence of a conductive layer, like salt water, beneath the surface. If Callisto has an ocean, it's likely buried very deep, perhaps 100 to 150 kilometers down, under a thick ice crust. The ocean might be kept liquid by a bit of residual heat. and perhaps some ammonia in the water acting as antifreeze. Could life be hiding in Callisto's putative ocean? Most scientists think Callisto is a long shot. It's further from Jupiter, so tidal heating is minimal. It's not in a resonance like the others, so basically it's not being flexed. Without much energy input, it's hard to imagine vigorous activity in its ocean to provide nutrients or energy for life. Also, if the ocean is sandwiched between thick ice, it may be in contact with an icy seafloor, not a rocky one, so no hydrothermal vent action. Callisto's ocean, if it exists, could be a cold, possibly slushy water layer that has persisted simply because the ice above is an excellent insulator. Life would likely need some chemical energy source. On Callisto, that seems lacking. The surface has some dark material, possibly primitive organic compounds from cometary impacts, but whether any of that mixes into an ocean is uncertain. From an exploration standpoint, though, Callisto has a perk. It's far from Jupiter's radiation. Callisto orbits approximately 1.8 million kilometers from Jupiter, which puts it mostly outside the harshest radiation belts. In fact, one NASA study once speculated that if humans ever set up a base in the Jovian system, Callisto might be a good choice because of this safer radiation environment. It's the most benign of the Galileans in that regard. You could imagine a research station on Callisto's cratered plains, studying Jupiter from afar. But that's far future. For now, robotic exploration will do. JUICE will also perform flybys of Callisto to better understand its composition and look for signs of that ocean. In terms of life, it's safe to say Europa is the front runner. It has the ingredients: water, chemistry, and likely energy, tidal heating, possible seafloor volcanism, that could make its ocean a habitable environment. Ganymede has water and some internal heat, but is more of a question mark for habitability due to the stagnant, buried nature of its ocean. Callisto has water, but probably very little energy. It's the most sleepy of the trio, geologically speaking. None of these moons have known life, but they give us a tantalizing possibility that icy moons can be ocean worlds. A completely different paradigm from Earth, which has a surface ocean warmed by the sun. If life can exist in the dark oceans of Europa or Ganymede, it would mean life doesn't need an Earth-like climate at all. It just needs water, chemistry, and time. That would hugely broaden the places we might find life in the universe. From a future exploration point of view, these moons are prime targets. In the coming decades, Europa Clipper and JUICE will vastly increase our knowledge. Perhaps they'll even find indirect hints of biology, say, complex organic molecules in Europa's plumes, if plumes exist and are sampled. Even if they don't, just confirming the conditions and environment will tell us how habitable these worlds are. And who knows, one day, a robotic submarine might swim in Europa's ocean, or astronauts might set foot on the icy surface of Ganymede or Callisto to drill for samples. Jupiter's moons represent our best chances in the outer solar system to find life. As one NASA slogan puts it, follow the water. And Jupiter's big moons have lots of water, making them extremely compelling in our search for life beyond Earth. 6. Exploring Jupiter. What Galileo, Juno, and other missions have discovered. For centuries, Jupiter was observed only from afar, a bright, banded disk in telescopes. It wasn't until the space age that we could truly unravel Jupiter's secrets up close. Over the past decades, several missions have flown by or orbited Jupiter, each adding pieces to the puzzle of Jupiter's interior, atmosphere, and moons. Let's take a journey through some key missions and their discoveries. Pioneer 10 and 11, 1973 to 1974. These were the first spacecraft to visit Jupiter. They were trailblazers, checking that the asteroid belt was traversable and that Jupiter's radiation wouldn't instantly fry a spacecraft. Pioneer 10 returned the first close-up images of Jupiter, showing its colorful clouds in greater detail. The Pioneer missions confirmed Jupiter's powerful magnetic field and intense radiation belts, and they discovered that Jupiter has an extremely large magnetosphere, extending far beyond what was expected. They also observed Jupiter's Great Red Spot and found it cold in infrared relative to surroundings, and they detected plasma in Jupiter's environment. Pioneer 11 even imaged the polar regions as it flew by and gave hints of a thin ring, though the ring's definite discovery came later with Voyager. These early missions were quick flybys, but they set the stage by showing Jupiter is approachable and scientifically rich. Voyager 1 and 2, 1979. The twin Voyager spacecraft performed transformative flybys of Jupiter. Their discoveries were astonishing. Voyager 1 discovered Jupiter's faint ring system, a thin set of rings made of dark dust particles, a big surprise since Saturn's rings were known, but no one suspected Jupiter had rings until then. But perhaps the most dramatic find was on the Moon, Io. Voyager 1's images revealed active volcanoes erupting on Io's surface, the first time active volcanism was seen beyond Earth. 9 volcanoes were observed spouting material hundreds of kilometers high. This showed Io to be the most volcanically active body in the solar system, reshaping our understanding of moons, that such a small body could be so geologically alive. Voyager 2 followed a few months later, taking more images and measurements. Fortunately, after Voyager 1's discovery, they reprogrammed Voyager 2 to look more closely at Io's volcanoes. The Voyagers also gave us our first good looks at Europa, Ganymede, and Callisto. They saw Europa's smooth, icy surface, crisscrossed by strange, linear cracks, which immediately raised the possibility of an ocean beneath. Even back then, in 1979, some scientists suggested Europa's surface resembled a cracked ice pack over water. They mapped Ganymede's mixture of old and young terrain and found it had odd grooves, possibly from tectonic-like activity. They saw Callisto's heavily cratered ice, including a giant bullseye crater called Valhalla. The Voyagers studied Jupiter's atmosphere in detail, revealing dozens of smaller storms, lightning in the cloud tops, and whirling white ovals. They also measured composition, finding, for example, that Jupiter's atmosphere is mostly hydrogen and helium with traces of methane, ammonia, etc. Importantly, they also noticed that the amount of helium in Jupiter seemed a bit lower relative to hydrogen than the Sun's composition, which later was confirmed by Galileo's probe, a clue about Jupiter's internal processes. In sum, the Voyagers turned Jupiter from a fuzzy disk into a rich system of worlds, gas giant with complex weather and 4 unique moons that looked like a mini solar system in themselves. Galileo Orbiter and Probe, 1995 to 2003. The Galileo mission was the first to orbit Jupiter, and it was a workhorse of discovery. It also carried an entry probe that was dropped into Jupiter's atmosphere. That probe, in December 1995, plummeted through Jupiter's clouds with a parachute, directly sampling the air. It measured the composition of Jupiter's atmosphere, finding, for instance, a surprisingly low amount of water, 1/10 of what was expected, in the spot it entered. It also detected more heavy elements, like argon, xenon, carbon, sulfur, nitrogen, than predicted, suggesting Jupiter accumulated material from colder regions or certain icy planetesimals. The probe recorded winds of 450 miles per hour and kept transmitting for about an hour, as it descended about 150 kilometers before being destroyed by pressure and heat. Meanwhile, the Galileo orbiter spent 8 years looping around Jupiter, performing close flybys of all the Galilean moons. Galileo's discoveries are numerous. It confirmed Europa's subsurface ocean by measuring its magnetic field interactions and saw chaotic terrains that hinted at ice mobility. It discovered Ganymede's magnetic field, the first moon known to have a magnetosphere of its own. Magnetic data from Galileo also indicated Europa, Ganymede, and Callisto all likely have conductive saltwater layers, oceans, under their surfaces. Galileo photographed volcanic eruptions on Io up close and even witnessed a volcanic plume silhouetted against space. It found Io's volcanoes are extremely hot. Some lava temperatures were over 2,000 degrees Fahrenheit, hinting at different magma composition than Earth. Galileo observed Io's plasma torus, a donut-shaped cloud of ionized sulfur and oxygen from Io's volcanoes around Jupiter. It recorded Io's effect on Jupiter's auroras and magnetosphere, essentially confirming Io as a key driver of Jupiter's magnetic environment. Galileo also studied Jupiter's rings, finding they are continuously replenished by dust from meteor impacts on small inner moons. It even found a tiny new moon, later named Dactyl, around the asteroid Ida during its cruise, the first asteroid moon seen, though that's more a trivia. In Jupiter science, Galileo provided an enormous leap. It was the first to dwell in Jupiter's magnetosphere long-term, mapping its structure and dynamics. It saw that Jupiter's magnetosphere is a turbulent place with plasma waves, and it observed how it responded to solar wind changes. Galileo's top 10 science results, as listed by NASA, include measuring Jupiter's atmospheric composition and noting differences from the Sun, finding ammonia clouds and weather patterns, discovering Io's volcanism is 100 times more energetic than Earth's, truly putting Io in a class of its own, 73, and detecting the interactions of Io's atmosphere with Jupiter, like electrical currents linking them, 74, and of course, the evidence for oceans on Europa, and possibly Ganymede, Callisto, and Ganymede's magnetic field are huge findings. Galileo also revealed that Jupiter's rings are formed from dust kicked off of moons. On the interior side, Galileo's data suggested that Jupiter's core might be small, but it wasn't precise enough to nail that down. That would await Juno. Galileo had its challenges. A famous one was that its high-gain antenna failed to open, forcing it to send data via a low-gain antenna at painfully slow speed. But engineers salvaged the mission by compressing data and prioritizing important observations. By the end, Galileo had transformed our understanding of the Jupiter system. In 2003, with its fuel low and not wanting to risk contaminating Europa, the spacecraft was deliberately sent into Jupiter, burning up in the atmosphere it studied. Cassini, 2000, and New Horizons, 2007, flybys. These weren't dedicated Jupiter missions, but they did important bonus science during gravity-assist flybys. Cassini, on its way to Saturn, flew by Jupiter in late 2000. It took some of the most detailed global color portraits of Jupiter, often seen in books, and it made movies of Jupiter's cloud motions. Cassini's cameras and spectrometers observed Jupiter's atmosphere, confirming things like ammonia clouds and detecting an unusual dark oval storm that appeared in 1998, dubbed the Little Red Spot after it later turned reddish. Cassini also observed Jupiter's magnetosphere and collaborated with Galileo, which was still active, to do joint measurements, giving a broader picture of the magnetic bubble. New Horizons, on its way to Pluto, zoomed past Jupiter in early 2007. It took the opportunity to observe a major volcanic eruption on Io's Tvashta volcano, capturing an amazing image of a huge 200-mile-high plume silhouetted against space. New Horizons also mapped Eo's night side in infrared, seeing glowing lava lakes. It snapped the best view of the little red spot, a smaller red storm that had formed from merged wide ovals, and it conducted unique measurements of Jupiter's magnetotail, the long magnetic tail streaming from Jupiter, and studied interactions in the far reaches of the magnetosphere. These flyby contributions added some slices of knowledge, like filling gaps in time that dedicated missions weren't there for. Juno, 2016 to present. NASA's Juno spacecraft is the current mission orbiting Jupiter. Juno is special in that it is studying Jupiter's interior structure and polar regions in ways never done before. It arrived in July 2016, entering a polar orbit. Juno's key instruments include a gravity radio science system to map Jupiter's gravity field, hence deducing interior mass distribution, a microwave radiometer to probe beneath the clouds, magnetometers to map the magnetic field, and particle and field detectors to study the magnetosphere and auroras. And of course, Juno carried JunoCam, primarily for public outreach images, which ended up producing stunning views of Jupiter's pole and cloud tops, making the public fall in love with Jupiter's swirly artwork anew. What has Juno discovered? First, Juno flew over Jupiter's poles and took the first ever images of the polar regions. Instead of bands, Juno saw clusters of giant cyclones crowding around the poles. For example, at Jupiter's North Pole, Juno found 8 enormous cyclones arranged in an octagonal pattern around a central cyclone, each storm as wide as the USA or larger. At the South Pole, it initially saw 5 around one. Later, a 6th joined. These polar cyclones are packed tightly and surprisingly stable. They don't merge into one big storm, which was puzzling to scientists. Juno's data showed they are warm at the top and cold at the bottom, opposite to the Great Red Spot, which is cold at top, indicating they are cyclones versus anticyclones. The discovery of these geometric arrangements of polar cyclones was a big surprise. Nothing like that on other planets. Why do they stay neatly organized? That's still under study, but it may be that there's a sweet spot where the cyclones repel each other enough to keep their distance, but are kept in place by jet stream boundaries. Juno's gravity measurements have been revolutionary for understanding Jupiter's interior. By tracking how Juno's orbit is slightly tugged by mass concentrations, scientists deduced that Jupiter's core is not a compact, Earth-like core, but rather a fuzzy, extended core, perhaps 0.5 of Jupiter's radius in size. It seems Jupiter's heavy elements are spread out in a dilute core region, maybe 10 to 20 Earth masses of heavy stuff mixed with hydrogen. This suggests Jupiter either had a core that got partially eroded, mixed into the rest of the planet, or a huge impact early on might have shattered and dispersed an early core. This was a profound finding. It favored the idea that Jupiter did start with a solid core, consistent with formation models, but something stirred the pot to smear it out. Additionally, Juno measured a slight asymmetry in Jupiter's gravity field, which turned out to be due to its winds. Yes, Jupiter's jet stream belts and zones, which reach deep, cause extra mass distribution that affects gravity. By measuring this, Juno found that the zonal winds extend about 3,000 kilometers down into Jupiter before tapering off. In other words, Jupiter's familiar striped winds are not just skin deep, they involve a few percent of Jupiter's mass. That was much deeper than expected. We used to think maybe the weather was confined to the upper hundreds of kilometers at most. This also means Jupiter's interior rotates nearly as a solid body beneath that depth. The microwave radiometer revealed the structure of ammonia and other gases at different depths. It found that ammonia is very high at the equator, forming a sort of plume from deep down to high up, but drops off in the mid-latitudes. The notion of mush bowls came out of Juno data. Basically, in mid-latitudes, ammonia and water might combine to form a kind of slushy hail that falls and transports ammonia deeper, creating ammonia-poor air above. This explained why Galileo's probe found little water and ammonia. It descended in a rare hotspot region where dry air was descending, so Juno gave a more complete picture. Jupiter has weather layers and maybe a kind of rain of ammonia-rich hailstones in storms. Juno also looked at the Great Red Spot with its microwave instrument, finding that this giant storm extends roughly 200 to 300 miles, 300 to 500 kilometers below the cloud tops. This means the Great Red Spot is not just a shallow feature, it reaches deep into the troposphere. Juno's magnetometers found that Jupiter's magnetic field has some unexpected lumpy spots, notably a region near the equator called the Great Blue Spot, blue indicating stronger field in one polarity, which is a concentration of magnetic field that wasn't expected in a simple dipole model. Jupiter's field also showed signs of time variability, secular variation. By comparing to earlier flyby data, Juno detected that the magnetic field is changing slightly over time, especially around the equator, likely due to the deep winds stirring the magnetic field from the dynamo region. This is the first time we've seen the magnetic field of another planet change over a human timescale. Juno, with its particles and fields instruments, has made amazing measurements of Jupiter's auroras and magnetosphere. It discovered new auroral mechanisms, like that Jupiter can produce auroras via intense electric potentials, like on Earth, but also via diffuse wave-particle interactions. Juno observed high-energy heavy ions, oxygen, sulfur, being hurled into the atmosphere, causing X-ray aurora flares, and identified the process behind those pulsating X-rays as Jupiter's magnetic field oscillations. And when it comes to the moons, during its extended mission, Juno has flown by Ganymede, 2021, Europa, 2022, and is doing a series of Io flybys, 2023 to 2024. The Ganymede flyby yielded the first close-ups of that moon since Galileo, revealing new details of its surface, such as finer details in the grooved terrain and strange bright patches. Juno's instruments also probed Ganymede's magnetic environment and caught radio emissions from Ganymede's auroral currents. The Europa flyby in 2022 provided some of the highest resolution pictures ever of areas called chaos terrain, where blocks of ice have shifted, giving more evidence of the warm, under-ice activity. Juno's microwave instrument also tried to sense Europa's ice thickness and composition. And Io, Juno's recent flybys, have given us stunning IR images of Io's many volcanoes glowing, and Juno even witnessed the most powerful eruption ever recorded on Io in late 2024, detecting a huge new hotspot and a surge in infrared emission. This event showed Io's volcanism can reach incredible levels, that eruption outshone anything previously seen, releasing energy 6 times all of Earth's power plants combined. Juno's measurements of Io's interactions are shedding light on how Io's volcanism feeds Jupiter's magnetosphere. All in all, Juno has greatly expanded our knowledge of Jupiter's interior, fuzzy core, deep winds, atmosphere, global ammonia, water circulation, depth of storms, magnetic field, strong, uneven, slightly changing, and moons, refining what we know about Ganymede, Europa's surface, Io's volcanism. And it's not done yet. It continues to return data as it circles Jupiter, each orbit revealing a bit more. Each mission, from flybys to orbiters, has built on the previous. Today, we also have upcoming missions. Europa Clipper will focus on Europa, and ESA's JUICE will focus on Ganymede, with Europa and Callisto flybys, both due to arrive in the early 2030s. They will directly address many questions raised by Galileo and Juno, like how thick exactly is Europa's ice? What's the composition of the ocean? How habitable are these worlds? And what is Ganymede's interior like? Jupiter's system has been a playground for exploration, teaching us not just about Jupiter itself, but about planetary systems in general. For instance, Juno's finding of a fuzzy core has implications for exoplanets. Many gas giants out there might similarly have big diluted cores. The discovery of ocean moons has made scientists realize that habitable zones aren't just around stars. They can be around giant planets via tidal heating. In a way, exploring Jupiter is like exploring a mini solar system, with the planet as a sun substitute. Though not emitting fusion heat, it provides tidal energy and radiation, and its moons as diverse worlds. We've gone from Galileo Galilei's first look in 1610 at 4 stars around Jupiter to spacecraft mapping ice fissures on those moons and tasting Jupiter's magnetic secrets. And we're not done. Each mission writes a new chapter in the story of Jupiter, the king of planets. 7. Io, the volcanic powerhouse and its dance with Jupiter's magnetism. Among all the moons of Jupiter, Io stands out as the wild child, a world of fire and sulfur. Io is the innermost of the Galilean moons and is often called the most volcanically active object in the solar system. This little moon, about the size of our moon, is literally bursting at the seams with volcanoes. Over 400 active volcanic regions have been identified on Io. Lava fountains, lakes of molten rock, towering eruption plumes. Io is like a constantly erupting volcano world. Why is Io so volcanically active? The answer lies in the powerful gravitational relationship it has with Jupiter, and to a lesser extent, Europa and Ganymede, a phenomenon called tidal heating. Io is caught in a titanic gravitational tug-of-war. As it orbits Jupiter, once every 42 hours, Jupiter's immense gravity tries to keep Io in a circular orbit, but Io is also in a resonance with Europa and Ganymede. For every 4 Io orbits, Europa orbits 2 times and Ganymede 1 time, so they line up periodically. This resonance means Io's orbit is slightly elliptical, not perfectly circular. So sometimes Io is a bit closer to Jupiter, sometimes a bit farther during each orbit. This causes Jupiter's gravitational pull on Io to vary. When Io is closer, it's pulled a bit more. When farther, a bit less. The result? Io gets continuously squeezed and stretched. It's like if you took a ball of clay and kept squishing it, that generates internal friction and heat. Inside Io, this tidal flexing generates enormous amounts of heat, enough to melt rock into magma. Io essentially has a magma-rich mantle, and that magma forces its way up through Io's crust, erupting as volcanoes. It's as if the whole moon is a giant pumping heart of volcanic activity powered by Jupiter's gravity. How powerful are Io's volcanoes? Extremely. Some eruptions blast material 300 kilometers, about 190 miles, above the surface. The energy output of Io's volcanoes in total is orders of magnitude greater than all Earth's volcanoes combined. For instance, the Loki Patera volcano on Io, a huge lava lake, alone can emit more power than all of Earth's active volcanoes. Io's lavas are also unusual, very hot, likely basaltic or even ultramafic, magnesium-rich lavas, hotter than Hawaiian lava by a few hundred degrees. In 2024, as mentioned, Juno observed the most intense eruption ever seen there, in Io's South Polar region, which was pumping out 6 times the energy of all of Earth's power plants. Imagine a volcano so fierce that it could outshine a small country's nighttime light if seen from space. Io's surface is a constantly changing canvas. It's modeled yellow, orange, and white from sulfur and sulfur dioxide frost. Volcanic deposits can paint large areas. For example, Io's giant plume from the Pele volcano left a big red ring of sulfurous material on the surface. Because Io is continuously resurfaced by volcanoes, it has no impact craters. Any crater that formed gets buried or erased quickly on geological timescales. In contrast to icy moons, Io's surface is rock and sulfur. In fact, solid sulfur and sulfur dioxide snow are present from volcanic outgassing. Io's atmosphere is an extremely thin waft of sulfur dioxide gas that comes from the volcanoes. It's so thin, it's basically a surface-bound exosphere, and it collapses when Io goes into Jupiter's shadow. The gas freezes onto the surface until sunlight returns. Now, Io doesn't just do its volcanic thing in isolation, it strongly interacts with Jupiter's magnetic field and environment. Io is essentially the key piece in Jupiter's electromagnetic dance. Here's how. Io's volcanoes emit not just lava and solids, but also copious amounts of gases, mostly sulfur dioxide. When these gases escape Io, some portion becomes ionized, stripped of electrons, by solar radiation or by collisions. Io is embedded in Jupiter's magnetosphere, so once the gas is ionized, the charged particles feel the influence of Jupiter's magnetic field. Jupiter's magnetic field rotates along with Jupiter. Remember, Jupiter's day is just under 10 hours, so the magnetic field is dragging around. Io orbits more slowly, 42 hours. So to the magnetic field, Io is like a rock in a river of magnetism. The relative motion causes an electric field and currents to flow. Io effectively generates an electric current with Jupiter. Roughly a 5 million amp current flows along magnetic field lines from Io to Jupiter's polar regions. This is often called the Io-Jupiter flux tube or electrodynamic coupling. It's like Io is a conductor moving through a magnetic field, creating a circuit. When those currents slam into Jupiter's upper atmosphere near the poles, they make auroras, specifically bright auroral spots called Io's footprint and trailing auroral arcs that Hubble and other instruments have observed. So Io actually causes a kind of bullseye aurora on Jupiter. No other moon in the solar system does this so dramatically. Europa and Ganymede also create auroral footprints, but Io's is the brightest. In addition, the ions from Io's volcanoes form a torus, a donut-shaped ring of ionized sulfur and oxygen that surrounds Jupiter roughly at Io's orbit. This Io plasma torus glows in UV light. It's basically a ring of charged particles co-rotating with Jupiter's magnetic field, and Io continually feeds it with fresh material. Over time, these particles can diffuse outward, some reaching the outer magnetosphere or escaping, and some also falling along field lines to produce auroras. Io's activity thus is a major source of plasma for Jupiter's entire magnetosphere. Without Io, Jupiter's magnetic environment would be much emptier. In fact, Jupiter's powerful radio emissions, those decametric radio bursts discovered in the 1950s, are known to be tied to Io. They occur when Io's flux tube interacts in certain ways, producing radio noise that we can detect here on Earth when the geometry is right. Scientists sometimes refer to Io as a particle accelerator for Jupiter. As Juno recently observed, Io can even flinging heavy ions back and forth. Juno's Jade and Jedi instruments detected high-energy protons traveling from Jupiter back toward Io along field lines, basically some of the auroral current particles reflected, which was a new observation. This phenomenon is helping us understand wave-particle interactions in the Io flux tube. Io, by dumping mass into Jupiter's magnetosphere, causes all sorts of plasma physics effects. It can trigger plasma waves, modify the magnetic field, and even influence the overall shape of the magnetosphere. So, Io interacts with Jupiter's magnetic environment in two main ways. One, electrodynamically, generating currents and auroral footprints. Think of it as literally connected to Jupiter by magnetic field lines like a circuit wire. And two, mass loading, supplying material, ions, that become part of Jupiter's magnetospheric plasma. The consequences of these are substantial. The constant mass loading by Io is why Jupiter's magnetosphere is swollen and full of sulfur and oxygen ions. Those ions cause Jupiter's magnetosphere to be rotationally driven. It's like a huge flywheel, and the coupling to Io actually slows Jupiter's rotation very, very slightly over time by transferring angular momentum to the ions, which then eventually escape, effectively transferring energy to the plasma that leaves. The auroral footprints of Io and Europa, Ganymede, are unique multi-world interactions we can observe, a glowing sign that Io was here on Jupiter's poles. One could ask, does Jupiter's magnetic field do anything back to Io? Yes, Io is embedded in radiation. Io gets blasted by the charged particles it helps create. That means Io's surface is irradiated strongly, potentially altering its surface chemistry. Io's surface is mostly sulfur compounds, and it's in such flux geologically that radiation effects may be quickly buried by new lava. But still, Jupiter's magnetic field also induces an electric field across Io's diameter of around 400 kilovolts. That's part of what drives the current. So Io experiences electromagnetic forces. If Io had a substantial metal core or magma ocean, Jupiter's changing field might even induce currents in Io. Some studies suggest Io could have a magma ocean layer electrically conducting, which helps complete the current circuit. In summary, Io is volcanic because of Jupiter's relentless tidal squeezing, making it a hellish world of lava lakes and giant eruptions. And Io is intimately connected to Jupiter's magnetosphere, effectively acting as a generator and plasma source. It's like Jupiter and Io are connected by invisible wires. When Io's volcanoes erupt, they not only reshape Io's surface, but also brighten Jupiter's auroras and fill its space environment with charged particles. Io truly earns the title of the most volcanically active body, and it showcases the fascinating interplay between a planet and its moon, gravity heating the moon, and the moon's activity feeding the planet's magnetic phenomena. In the grand ballet of the Jovian system, Io's fiery dance drives an electromagnetic rhythm that makes Jupiter's domain one of the most dynamic places in the solar system. The Sleepy Scientist's Introduction, a bedtime journey to Jupiter, spoken in a soft, lullaby-like tone. Hello there, young stargazer. Tonight, let's take a dreamy journey far, far away, beyond the moon and planets you know, out to the realm of the mighty Jupiter. Close your eyes and imagine the night sky glittering with stars. Among them is a bright wandering star, that is Jupiter, the king of planets, watching over the night. As you breathe slowly, picture yourself drifting up from your cozy bed, weightless, into the starry sky. The earth grows small below you. Gently, you sail through silvery moonlight and into the deep dark of space, headed toward a golden pinprick in the distance. That golden white beacon grows larger and larger until you realize it's not a star at all, but a gigantic banded planet, Jupiter, swirling with colors like a marbled jewel. Now you are floating above Jupiter's wispy cloud tops. It's peaceful from up here. You see broad stripes wrapping around the planet, and a great red oval storm slowly turning. Imagine the clouds of Jupiter below, cold and windy, painted in sunset shades of orange and cream. They form mesmerizing patterns like frost swirls on a window pane. In our minds, we dive a bit lower, not too far, just enough to see the top of Jupiter's endless clouds. We're perfectly safe, floating as if in a dream bubble. The cloud bands drift past, and tiny white ammonia clouds puff like meringue. There's no land, no ground, just an open expanse of sky going down and down. Jupiter turns beneath us, unhurried and grand. In the distance, 4 sparkles orbit Jupiter, the big moons, our travel companions. Let's gently glide toward one, the bright ice ball of Europa. We fly over its surface, a smooth, icy plain crisscrossed by long cracks. It's quiet here. The stars twinkle above Jupiter's shoulder, casting a gentle light on Europa's frozen crust. Beneath those ice ridges an ocean sleeps, perhaps hiding secrets of life in its dark seas. As we pass into Europa's night side, we look back and see Jupiter looming on the horizon, a gigantic striped globe hanging in a black sky, lighting Europa's ice with a faint twilight glow. Magical. We continue on, our little dream spacecraft coasting without a sound. Next, we visit Ganymede, the largest moon, with patches of light and dark on its ancient face. Ganymede has its own faint glow, a protective magnetic hug that shields it. We wave hello and move on to cratered Callisto, on the fringe of Jupiter's domain, an ancient and quiet world dotted with rings of impact marks. Callisto seems like a wise old guardian, keeping a respectful distance from Jupiter's hustle and bustle. Finally, we dare to approach fiery Io. Can you feel a faint warmth? Io's surface glows here and there with the red-orange light of active volcanoes. Suddenly, from one volcano named Loki, a gentle fountain of lava sprays up, but in the silence of space, it's like a silent firework, beautiful and not frightening from our safe vantage. A plume of sulfurous gas drifts up, painting the sky around Io. This plume will make its way to Jupiter's magnetic field, but hush, that's a story for another time. We drift onward. Our journey takes us above Jupiter's north pole now. Look at that, a soft green-blue aurora dancing around the pole, like curtains of light swaying in a cosmic breeze. They shimmer quietly, wrapping Jupiter's dark pole in a serene glow. These northern lights of Jupiter are hundreds of times brighter than Earth's, but from here they seem like gentle night lights for the giant planet. We listen in our imagination. Perhaps Jupiter sings with radio sounds, but to our ears it's just a calming silence, the feeling of enormity and calm. As our tour comes to a close, we find ourselves bathed in the pale sunlight reflecting off Jupiter. We have danced among giants. We felt Jupiter's mighty presence, but we also saw its peaceful, protective side, shepherding moons, absorbing wayward comets, wearing a crown of auroras. It's time to head home. In the blink of an eye, our dream carries us back across the cosmic ocean, back to our own lovely Earth, where we slip gently through the atmosphere and find ourselves snug in bed once more. The stars outside your window twinkle, and maybe Jupiter's among them, watching over you from so far away. Though Jupiter is colossal and powerful, tonight it was our friendly guide through the cosmos. Feel the wonder of how vast space is and how astonishing its worlds are. Now, let your mind drift like a spacecraft coasting among stars. Dream of swirling Jupiter and its moons dancing in the night. The universe is grand and full of stories, and you are a beloved part of it. Sleep well, young explorer, under the same stars that shine on Jupiter. Sweet dreams of cosmic journeys and gentle giant planets.